Good afternoon, everyone. Thank you for joining Megger Asia webinar. I'm Grace from Megger Hong Kong. Today, our topic is relay protection test challenges in renewable power plants and grids. Presented by Mr. Stefan Larsson, who is the relay product manager from Megger Sweden. This is a live webinar. You're automatically muted to prevent any background noises. During the webinar, if you have any questions, please type into the question box, which you can see on the left of your screen. We'll answer your questions in the Q&A session. At the end of the webinar, please help us fill in the survey, which is on the right-hand side. We'll be sending the presentation materials to those committed the survey. Attendees will be able to download an attendance certificate after they have finished the webinar and completed the survey. And the recording of this webinar will be sent to you in 2 days' time by email. So without further delay, let's start now. Thank you for joining us today. Stefan, I'll pass the time to you now. Thank you.
Thank you very much, Grace. Yes, so my name is Stefan Larsson. I'm the product manager for protection test, working from Megger, Sweden. And I have been working with Megger as a product manager in 13 years. And I started my career on ABB, where I was working as a relay and control designer and also as a commissioning engineer. So I was on ABB in 9 years. And after that, I was working in 17 years, actually, on Schneider Electric, working as a product manager for relay protection and also medium voltage. And today, as Grace said, we are going to speak about the challenge to test relay protections in renewable power plants and grids. So that's the main part for this presentation. And of course, I will speak about the Spherical 900, who can manage this very well in this kind of power stations. So we have a very short overview of the Spherical 900. It's a toolbox for testing substations, and you can generate and test three-phase protection with that one. It's also for, it have 3 currents and it have 4 voltage generators. And it's a complete standalone functionality, which means you don't need to hassle with the PC and have problems to communicate in between. So it's always the unit itself where you can bring to the substation and do your testing. And it's very rugged and reliable for field use. So it's made to be on the field in the substation. And it can generate 900 volts and also 105 amp if we put the Spherical in the single phase mode. So it can go very high in the amplitudes. It is very unique and could be good if you want to test with the Spherical 900 for primary testing. But also, of course, you can go in 3-phase mode and put the generators to generate individual. Then it's very good for doing secondary testing on relays, meters, transducers in the substation. So Spherical 900 is a complete toolbox, as we said, for testing the substation. You can use it for doing wiring checks. Also, you can use it for testing the signal stations up to the SCADA, the dispatch center, checking from relays and meters up to the SCADA to simulate the power, for example, or energy for an energy meter. It's also possible to do primary injection. We can do phase angle measurements with the Spheric 900, measuring direct from the switchgear, for example, in between one voltage and one current. We can do polarity tests when we are testing voltage transformers and current transformers. Also burden measurement and ratio test with current transformers and voltage transformers. Also, we can do the CT magnetization test on the current transformer to find out the voltage knee point, for example. But of course, we can also do protection relays test. So actually, that's the main function with the Spheric 900, but not the only function. So Spheric 900 can do a lot in the substation. Now, if we go to the new renewable power plants which are coming, with that the network are going to change, and we have, for example, wave power is coming. We have wind power, and this is a picture when I was visiting a wind farm in Sweden. It was now I'm standing 120 meters over on the tower, over the ground, and when I was there, we was testing the relay protection, which was in the bottom of the tower, and we was testing it with the Spheric 900. Also, I actually was visiting a solar farm. It was actually 3 solar farms in Kenya. They was quite big. There was each one was on 30 megawatt, and yeah, it was quite a lot of power produced from these 3 substations. And again, we could see how they was using the Spheric 900 to test this substation. So with the renewable energy power, it's coming also more and more storage system, like stored batteries from homes or industries, companies, or also installed in the network. Also, we have the V2G, the vehicle to grid, when you can also take the power from the battery power from the vehicle to the grid. So it's a lot of different sources going to be connected to the network that make a lot of changes in the network. So with the new distributed power plants and smart grids, it will be less batteries in the substation, in the small power substations. So with that, it will come more and more self-powered relays. And that I will speak more about today. Also, in the smart grids and distributed power plants, they will require frequency protection, like over frequency, under frequency, and rate of change of frequency, the rock-off protections, for example. Because the frequency is very important to have a stable network and a stable supply in the network when you not to have big outages in the network. So actually, Spheric 900 is unique in testing frequency protection and self-power protections. So this is one of the main parts I will speak about now, and it was actually a standard was launched in year 2019, and that standard was about the functional requirement for frequency protection, IEC 60255-181. And this new standard tells how the relay protection the algorithm shall measure the frequency. And also it tells how the relay test set should be simulating and how to do when you injecting the frequency change in a relay protection. And this new standard was reflecting the reality, actually, what you have in the network when the power generator is going to increase the frequency, or the power generator is going to decrease the frequency. So it was the main thing with this frequency, to make a standard to be equal all over, from the relay test sets to the relay. Also, I will speak about this to test the self-powered relay, which is a challenge, because self-powered relays drain the energy from the secondary current through the AC-DC converter in itself in the relay. The energy conversion generates harmonics that must be absorbed by the test set. So that's the challenge when you're testing a self-power relays, because it takes the power from the current transformer and it need this current not only for measure, it need it also to be live and be able to work. So if we are in a power system, the system frequency is not constant anymore. So the electromechanical power system contains less and less mechanical inertia, stored rotation energy. So inverter-based generations, which are coming more and more nowadays with the distributed power plants, they are considered as zero inertia, like the wind power, photovoltaic, battery storage. So high variations of produced power because of the weather, the frequency could actually change. So you need to have a balance in between the supply of the power and the demand, the load management. So that's very important nowadays, and that's why we more and more go to try to have smart grids which are more functional. So we have the new standard in testing frequency protection and about frequency relays. So the frequency relays, in the past it had been like this. The frequency relays from the different manufacturers have responded to the same frequency variation in different ways while they have the same settings. So these have been a problem, because from testing one manufacturer with the same settings, you could have one result. Testing another manufacturer of relay, you can have another result. So actually it was very confusing. It is very confusing still to test frequency relays. But with this new standard, it will help you to make everything equal in terms of relays, and also in terms of how to simulate a frequency change from the relay test set. So one thing which are important when a relay test set are doing a change in the frequency, when you're simulating a change in the frequency, one important thing is that the relay test set shall not introduce a phase shift. Like here on this picture, we can see a simulation, which is very common when testing over frequency protections. You have a pre-fault state and a fault state. You simulate, let's say, for example, 50 hertz, and then you suddenly go to 53 hertz. And then you will see if the relay are reacting, and you're measuring the time. If you're doing that, the relay, because this is not a realistic change in the network, the relay could measuring very wrong result. You will have a wrong result. That could be possible depending on what kind of manufacturer it is who have made this relay. So it's very confusing to do this. Also, in this standard, it should be formalized, the meaning of a variable frequency. So it should be very smooth change, which means that when changing, it should not, the frequency, it should not be suddenly, it should be smooth to make a realistic change according to what we have in our networks. So when you make a ramp, and that's what we recommend to use when testing frequency protection, to use the ramp function in the relay test sets. This ramp should be smooth, and that means that the frequency should be changed in microseconds when you're ramping. It should not be changed in pieces, like in milliseconds, for example, every cycle or every half cycle or something like that, like a staircase. That's not allowed according to the new frequency standard. So this is one important thing when you make from the relay test sets, when you simulate a frequency change. It should be very smooth. So also when you're testing frequency protection, for example, over frequency, you maybe start from the nominal frequency, let's say 50 hertz, and you set the speed of the change, in this case 0.5 hertz per second. Then you run the ramp, you run the ramp and the frequency change, and then you will reach the set value of the frequency protection, and the frequency protection will start. And then you will reach the operation of the frequency protection output, and then you stop the timer. And then you will have the time for the frequency protection. So this is the recommendation from this standard, how to do a frequency change. You shall do it in the ramp instrument to make a ramp, and you shall not do it as a sudden change like pre-fault fault. So that's common, what to recommend here. And if you are using the Sverker 900, you will have the possibility in the ramp instrument. You set the ramp and run it, and then you have the possibility to measuring the time. So it's very easy to do this in the ramp instrument with the Sverker 900. So we have make application note, which you can find on the Megger webpage, for example, about how to test frequency relays according to the standard IEC 60255-181. So you can read this everything about this, how to test with the Zwickey 900 frequency protection. So that's important. Also, we have now we're going to the next challenge when you're testing relays, and that's the challenge which are coming more and more with the self-power relays. So in the past, we have very simple and cheap relays, which didn't need to have any DC power. And this only need to, they was running on the current from the current transformers. It was the electromechanical relays. So the idea is good, and the energy from the measured secondary quantities, so that's what's working. But they required very periodic maintenance and they didn't have any possibility to communicate to SCADA or RTU. They are not numerical with no self-supervisions, no communication, no different setting groups and so on. So it's a lot of disadvantage with this. And they are also big, and they are not cheap anymore, actually. Anyway, no doubt, they are a beautiful piece anyhow of equipment from the past. So nowadays, we have the self-powered relays, digital relays. They are a reality. And here we can see some different manufacturers of self-power relays. So self-power relays is it's a test challenge, of course. The first thing you need to have power from the current generator when you test the self-power relays. So, self-power relays drain the energy from the secondary current through the AC-DC converters. So the energy conversion generates harmonics that must be absorbed of the test set. So when the relay test set generates, it's a lot of distortion of this sign in the sinus wave, and this will make could be making wrong readings in the protections. So that's a big problem, because you set, for example, on 1 amp to run it from the relay test set, but actually the relay is measuring 0.7 amps. And you will get wrong result, actually. So also the challenge with testing self-power relays are the highly non-linear and time-varying load, and the control circuit must be able to keep the injected current constant with this non-linear and time-variant load. So that's the tricky thing with this. And with the Zwickey 900, we have the opportunity to test three-phase also, because normally that's the best way to test the self-power relays, because then it can take power from all the three phases, which it's helping the self-power relays more to get the power to itself. But with Zwickey 900, it's possible to run in single-phase mode also with the current generator. And single-phase mode means that we connect the current generator in series or parallel. And if we do that, we increase the power 3 times, or we increase the current amplitude 3 times. So it's a summation. So that's an advantage. We have a very good flexibility to test. And also we can, of course, run it in medial. The current generator is in medial mode, and then we get and do the free-phase testing. So we have a lot of flexibility with the Sverker 900 when testing self-power relays. Another thing which is very important when you're testing self-power relays is the binary input, because self-power relays are able to deliver the energy to trip. So it is the relay itself who deliver the energy to the striker in the circuit breaker, to the shunt tripping coil in the breaker, and that needs power. So we have some other additional accessories. They are able to accumulate the energy trip from a conventional tripping coil. So this voltage and this power from the output trip on the relay should the relay test set be able to detect. So that's important. And with the Sverker 900, we can be able to set the voltage on the binary input. Also, we have a debounce filter with the settable time, because sometimes the self-power relays is giving a spike voltage before the tripping coming, and that could be disturbing also. So if you have a filter to filter the output and the tripping output, and that we also have in the Sverker 900, so that's very good. So amplifier needs to be robust against harmonics and protected against harmonics, not to destroy the relay test sets and the transistors in the relay test sets which are generating the current. So that's very important. Also, it's important to have advanced and adaptive non-linear real-time control loops for controlling the current generators when you have a lot of disturbance. So it must be possible to test the self-power relays also have in the free-phase environment, because sometimes you need that. You don't succeed to test the self-power relays maybe with the one phase, single phase. So in the Sverker 900 we also have the possibility to have a graphical visualing in the Sverker 900 to see where the test point is for an inverse curve, for example. So actually, when testing self-power relays, no special setting or configurations is done, because everything is there in the unit itself. We have taken care of this when we was developing the Sverker 900. And also it's easy to use and to run. It's the advantage with using the Sverker 900. We have also made a technical guide, for example, how to test self-power relays with Sverker 900. It describes how to do, and it's regarding two self-power relays called VIC1 and VIP1. So this you can find on the Megger website. So the good thing with the Spheric 900 is that it is very user-friendly. So you don't need to have any special training to use it if you're a relay technician guy and have worked with this before. It's high-speed testing. It will be time-saving, and it's good feeling. It's like driving a car. A few settings and to set before running the test, and it's with direct response. So it will go very quick. I will now go through some more functions in the Spheric 900 and the control panels. So some more information about Spheric 900, and you are controlling it from the front, the touch screen, and you have a knob. You can manually increase or decrease amplitudes of voltage, current, or frequencies, or phase angles. Also, you can connect a mouse or a keyboard in the USB port. If you would like to change voltage generators or current generators, you can do that to put them in series mode, or you can put them, for example, like here we have the current generators. They are connected in parallel mode. So you have an output of 105 amps, but you can go in series mode and you can go in three-phase mode like individual generating. And here we have the voltage channel. You can be, in this case, it's in series mode. Then you can deliver 900 volt from the generators. But we can also be in parallel mode. We can be in individual mode, three-phase mode. So if you are in individual mode with the current generators, we can run on each generator up to 35 amps on each generator. And if you are on voltage individual mode on the voltage generators, we can run up to 300 volt on each generator. So, and practically when you're changing from serial mode, parallel or individual mode, you're using the jumpers, which is coming together with the Spheric 900. So we have also 4 binary inputs, and we have 2 binary outputs, normal open, normal close. Could be used for simulating a breaker, for example, when testing auto reclosing. We have a multimeter. Everybody who knows the Spheriker one-phase tester, Spheriker 750 and 780, we have the same multimeter there, ammeter, voltmeter, and they could calculate in between each other like impedance or cos-phi or also phase angles in between these 2 inputs. We have an extra timer, could be measuring an extra time, for example, on the auxiliary contact or whatever. So this is the start input for that, and this is the stop input for that timer, and it's always accessible here this time. And the current and voltage is always accessible here in the bottom of the screen, voltage and current. And you can see like impedance and this other measurement calculated from these 2 if you push here on these arrows here. So from this USB port, you can also load the test reports. We have one in CSV format, and we have another one in another format, so it's 2 files. With the other one, together with the piece of software called Spheriker Viewer, you can get the PDF format on the test report, and it could also have graphical. You could also show graphical results in that Spheriker Viewer PDF format. We have three models of Sverker 900. We have the basic, we have the standard, we have the expert one. So basic is including the main and pre-fault fault. The standard one is also including the ramp, sequencer, and the CT magnetization. And the expert one is including all, and that's also including the impedance instrument, which could be used for testing distance protections, for example. It's like manual testing of a distance protection. So this is how the home menu looks like on Sverker 900. This is a file manager for test reports. Here is the configuration of the generators, and here is the system configuration of data time and language and so on. And always you can see in the bottom, you can see the ammeter and the voltmeter, and also the extra timer is here. So this is how it looks like. And now I will go through this 6 instruments very shortly. So we have the main instrument. It looks like this. You can do timing test. You can do determination of pick up and drop off of a relay, tripping contact. You can just set and inject and measure a voltage current, whatever you would like to do. It's very easy to work here, very understandable, user-friendly. And here is the measuring of the time, for example. If you would like to save test, you save it here. If you would like to open a save test, you can open it from here. Here is the pre-fault instrument. Looks like this. Here you set the pre-fault wireless here. So you push there. And then you set the fault wireless here. And how long time, for example. And then you're ready to go. You push here. And then when you would like to play this, you push on the play button. So that's a pre-fault simulation. And you will have the time, tripping time, for example, here, if you're measuring the time. This is when you're testing current transformer and doing a CT magnetization test. So you do a magnetization curve to find out the voltage knee point of the current transformer. So you can be in automatic mode. In the automatic mode, you just push the play button. You connect, of course, according to what the screen say, how you shall connect. And then you push the play button, and then you will start injecting the voltage. It will go up the curve, automatic, and when it finds the voltage knee point, it will go down, and then it will do a more precisely calculation of the voltage knee point. So when it's going down, he will show the voltage knee point, and then automatic he will do the demagnetization complete down to 0 for on the voltage, with the voltage. And then you're ready with the test. If you do manual, you use the knob on the Sverker 900, turn it up until the Sverker 900 in the screen will tell you to turn it anti-clockwise again, and then you need to push on the knob each time you would like to have where you would like to have the points. So when you do it manual, you need to active by yourself, push the knob to take the points, the test points. Okay, then we have a ramping instrument. This, for example, as I was telling about, is to be used when testing frequency protection. And the good thing is that you have the trip time here, so you can measuring the time here. So, for example, when you work with this instrument, you tell where to start. So you push here and tell where to start the ramp. Next step is to tell which speed and what you would like to change. For example, if you would like to change the frequency in the speed, or if you would like to change only the current or one current or voltage or even the phase angle. You can change whatever. That you will set here. Then you tell where to stop, and then you push here, then you're ready to go. And then you push the play button. And then you run this test. Okay. So then we have the sequence instrument. The sequence instrument is like the pre-fault instrument, but in the pre-fault fault we have only 2 states, and in the sequencer instrument we have 16 states. When you have that many states, you could do simulations like testing an auto recloser, for example, or restriking a fault, or motor start, or this kind of things. So it could be used when you need a lot of states to make a very long sequence. And then we have the last instruments, that the impedance instrument. That's where you can test distance protection, for example. So you're working in the impedance plane, and you're setting your values in impedance, resistance, reactance, or phase angle. And the Sverker 900 will calculate what kind of current and voltage it should generate according to your settings. So you set these values, whatever you would like, in the impedance plane, and Sverker will calculate by himself what voltage and what current he will inject into the, for example, distance protection. So it's quite easy. So Sverker 900 is very unique in the market because it can cover to test different load, different kind of hardware in the relay protections, because the burden could be very different in between what kind of hardware it is. So if you have the electromechanical relays, they are having a inductive non-linear. It is a inductive non-linear load, which is sometimes very difficult because you need to have a lot of power, and if you are on quite low current, like 1 or 2 amps, it's difficult to get that power at that very low current. But Sverker 900 can manage this. Static relays is difficult because it could be resistance, quite high resistance. Sophisticated numerical relays, they are very low resistance load, but the tricky thing with them are that they are very accurate, especially when you're testing on low current. You need to be quite accurate, and with the Sverker 900 we can deliver a very accurate current at very low current. For example, we can deliver 5 milliamps without any problems. So it's very sensitive and very accurate at low current, but it is very strong anyhow. So it's a combination of everything with the Sverker 900. And as I have been speaking about, the it can also test self-powered relays. So that's the unique thing with the Spherical 900. A lot of power, but also sensitive and being able to test accurate on low current. It's covering all kind of relays. We have also we have also a lot of application notes you can find on our web page. It's, for example, here we can see how to test negative sequence unbalance protection, how to test directional earth fault, how to test impedance measurement-based protection. This is how to test this distance protection. So this is how you can, and also we have how to test current transformer, all kind of tests you do on the current transformer, for example. So this is how you can use Spherical 900 to do different tests. And this is very appreciated. Also, if you go on the web page, you can find technical specification, data sheet, user guides, application notes. We have technical guides also and videos. So this is just a recommendation what you can find. We are now making a campaign for distributed energy resources, as we call it. And we have a landing page there where you can find testimonial videos. You can see about how to use Spherical 900 in photovoltaic plants. And application notes and these kind of things, podcast and whatever. Also, this is very good for you because we have on YouTube a channel where you can find informations, videos about Spherical 900, how to use it in the substation, how to use it in the PV plants. And also we have more than 50 how to do videos, how to test relays, current transformers, voltage transformers. So this was what I recommend. Okay, so now I must try to stop this. We shall see. Yeah, I shall do like this. And now okay, so I think yes, Grace. I don't know if we have some questions here.
Yes, all right. So now it comes to the end of the webinar. If you have any questions, you may type into the question box, which is on the left of your screen. And for those of you who are leaving, please remember to fill in the survey, which is on the right-hand side. And also, after you fill in the survey, you may download the attendance certificate, which is at the bottom control panel, the icon on the right-hand side. And we will spend about 5 minutes to answer any questions you may have. You can start typing into the chat box, so we will read out the questions for you. All right, Stefan, here we got the first question.
Yes.
Okay, it's asking, all self-powered relays giving distortion and measure wrong current when testing?
Yeah, all self-power relays have this problem, but more or less. So these relays, some of them can be very difficult to test, like if you inject, for example, from the relay test set 1 amp, you set 1 amp and inject it, then it's measuring like 0.7 amps. And if you're testing inverse curve, of course, you will have wrong time, and it will not be according to what you expect. So that's very confusing. So all self-power relays have actually this problem more or less from different manufacturers.
All right. And the second question we have is, can we synchronize 2 units together?
I mean, Sverke 900 is not possible to synchronize, and I really, I can understand maybe why the question is coming up, because they would like to have 6 current, maybe. That's the reason. But it's actually it's not possible to synchronize the 2 units. That's a problem. But what we don't know what's coming in the future, so that could be possible maybe.
Okay.
But not
and
now.
And the next question is, do you have power module for the Sverker 900 in cases like commissioning tests, considering that during commissioning tests, commissioning substation, for example, are not yet powered from the grid?
Okay. What I recommend, if they would like to have a power, we don't have a power unit from Megger, if I answer direct on the question. But what I recommend is that they buy one from, it's a lot of suppliers of battery inverters. You can find it very easy. And if they buy one, I will recommend that the power on that battery inverter is like 1.3 watt, 1,300 watt. That it could have the maximum power like that. Then it will be enough to do all the tests, and you will be able to deliver 105 amps, for example, maximum from the Sverker 900. So I know a lot of people which are using Sverker 900 or Sverker 750, which are using this kind of battery inverters, and they like it, and it's quite cheap to buy it from wherever, and they like it because always they don't need it. So if they don't need it, they don't need to bring it. So I mean, if you have it in the unit itself, the battery inverter, then you need to bring it all the time. Okay, that's the answer.
Okay, thank you. And the next one is, can the Sverker 900 be used for testing the differential line relay 87L with 2 Sverker 900s?
You disappeared a little bit, Grace. Can you repeat?
Yes. Can the Sverker 900 be used for testing the differential line relay 87L, which with 2 Sverker 900 together?
Okay, if it is a differential relay like pilot wire, then actually with it's not actually now it's not possible. But we are looking on it, and it's quite easy to arrange to have a GPS, and so I think within the future we will do that quite soon.
All right, okay. And the next one is, how to mitigate this error you mentioned while testing self-power relays, and what are the best way to test this type of relays?
Yes, how to, yes. Yeah, I mean, the thing, if you have this kind of error, I mean, when testing self-power relays, it is a problem because it's the relay test set who not can deliver the right current, actually, because it's too much distortion. So it's a problem to test self-power relays. You have a lot of distortion. I know in the past some relay manufacturers of self-power relays have some kind of a conversion table. I mean, to work with for when using a certain relay test set. But this is a problem. So with the Sverker 900, you don't have this problem, and this our message that yeah, if you use the Sverker 900, you don't have this problem. Everything works by itself, autonomous.
Okay, all right. And I think here is the last question. How do you test a differential relay seeing this unit only outputs 3-phase currents?
Yeah. Okay. As I said, if you would like to test differential relay, and if you would like to test the full characteristics, that means the characteristics of the bias curve in the modern relays, some of the modern relays, which have in the algorithm the zero sequence current, which some modern relays have, not everybody, then you need to have 6 current. But if this modern relay don't have it, or if it is an older relay, you can test phase like one phase, which means you inject 2 current and test the differential relay one phase. That's actually possible. But I know in some countries they don't test actually the bias characteristics even on a 6 on a differential protection, which are measuring the zero sequence current, because it's not. It's more. They think that it's more a test from the a type. It's more a type test, and it's not belongs to do a field test. But it's up to the customer to do it, and if they would like to do a full characteristics test on the modern relay protection, they need to have 6 current. Okay.
Okay, thank you, Stefan. I guess we don't have any more questions. If you have any questions later on, you can send us email to megger@megger.com, or you can also visit megger.com/webinars for future webinars. And just a reminder, please commit the survey and download the survey kit before you go. On next Thursday, which is 18th of May, we will have another webinar. Topic is keep your motor running. The time is 10 o'clock in the morning. So if you're available, you can go to our website to register for the webinar. So thank you again for attending. Thank you, Stefan, and also for the presentation, and also dancers Mark as well. So thank you all, and hope to see you again next time. Take care.
Thank you very much. Thank you very much for listening.